we were on storage encryption, and basically the key requirement in storage is that you should be able to read any block independently without reading from the beginning. So that rules out some of the modes of operation clearly. And second thing is that the encrypted text is available to anyone who is sharing the same disk. Although it is also available on the network that way, but you really have to work hard a little bit to get that text on the internet, on the wireless networks. On the wired networks it is even more difficult, but on the disk it is available very easily, and you know, you can get a long history of those texts. So IEEE sat down and said we need a special mode just for the storage, and they came up with this new mode called XTS-AES mode. AES obviously is the Advanced Encryption System, and XTS stands for XEX based tweaked code book mode, XT mode with cipher text stealing. So that is what XTS is. Now what is XEX? XEX was this mode which existed before all this, and that was called exclusive R, encrypt and exclusive R. So anyway, so all of these features are there in this mode. It has AES, it has tweaking, it has exclusive R, encrypting exclusive R, and it has cipher text stealing. Some of these terms we have explained before, and we'll go through them if not very clear right now. But basically the way it works is that you take a primitive element in Galois field 2 raised to 128, which is defined by the polynomial x. X is a polynomial, not a variable here. So x means, what is the binary number corresponding to that? X plus 0, binary number is 2. Yeah, 102. So that is the number 2, but in GF field, GF 128, and the polynomial is coming up in a minute, 2 raised to 128. So alpha raised to j. Every time you get a block, you raise alpha to the next power. So this becomes x raised to j. And then you take an initial value, or actually I here is the logical sector number. So each sector is assigned a number. It is logical sector number. It doesn't have to be starting with 0. It could start with any number, but normally it will start with 0. So that logical sector number is used as initial value. You encrypt it first with key K2. Okay, and K2 is equal to the size of the block. Remember, there are two sizes here. Size of the, when we talked about AES, we had AES 128, AES 256, AES 192. In those cases, those three numbers represented what? AES 192 was what? 192 was what? Size of the key. Size of the block in every case was 128 bits. Right? So that's what it is that whatever is the size of the block is the size of K2 here. So there are three keys. Actually, there are these keys, K2 and K1. K1 is where your AES key, and that would be 192, 128, or 256 bit long. And K2 is just used for this tweaking. So this is what exclusive R, encrypt and exclusive R means. You take the plain text, exclusive R with the tweak, encrypt it, and exclusive R again. This looks very similar to me to DES-X, right? In DES-X, Rivest had proposed that we do something like this, and that would give you a lot of keys. And in fact, he had, I think, two different keys here, so that would increase it, a lot more to power, right? But here we have the same tweak. Anyway, the tweak is random. Why it is random? Because we are putting the number through some kind of encryption, and the decrypted values, encrypted values are truly random, right? So, and then and the tweak is different for every block. How it is different for every block? Because alpha raised to j. J is the block number. I is the sector number. Each sector has many blocks. Block is very small. Block is only 128 bit. That is like 16 bytes. Right? The sectors are much bigger, maybe 512 or 520 or something like that bytes. So you have many blocks per sector. Right? So you take the sector number, sector number I, block number j, create the tweak, which is a random number, and then you do exclusive R, and then you do the, basically this encryption is a AES encryption. Okay, and in fact this is also AES encryption. So both of these are AES encryption, but this is with the size, which is 128-bit encryption, and this is 256-bit encryption. And so these are different size encryptions. So it is shown by the picture here. Let's look at the picture. You give I, and you give the key K2, and you do AES encryption that gives you, and then you, oh, by the way, this is not exclusive R, this is multiplication. X rather than plus. So you multiply it with alpha j. Now don't do that. Okay, what is happening here? Okay, so not do that. Okay, so this is alpha j. You multiply with alpha j, which simply means multiply by x raised to j, and then that gives you the tweak, and you use it at two places. You take the plain text, exclusive R, encrypt, and exclusive R. Alright, that gives you the ciphertext. Now the only thing left is what is ciphertext stealing. Now, if you remember from the last lecture on Monday, we talked about ciphertext stealing, and the idea was that you have two choices. If the last block is not full, you have the choice of either doing padding or doing ciphertext stealing. And the ciphertext stealing simply meant was that you take the last one block, and you take the last block which is incomplete, and you do some text shifting around. And we went through that on Monday, but I will go back again here. And it is just in the beginning of the same lecture. Alright, so the way ciphertext stealing works is that while this is true for all the blocks, but the last two blocks are handled especially. So this is PM-1 and PM. M is the number of blocks. And the way that works is that you take PM-1, do all the things, whatever you get at the end, you don't send all of it right away. You take the, PM, and then you take PM, you take the missing bits from the previous block, ciphertext, put them here, so this becomes a full block. Then you do the encryption, you get a full block, you send it first. In this case, you write it first. And then the leftover of the M- first block is written later. So the total size does not increase. If the sector size is 520 bytes, for whatever reason, it will remain 520 bytes total. Okay. Alright, so this is what is called XTS-AES mode, and you should understand every word here now. Exclusive R, encrypt, exclusive R, tweak, and this is a codebook mode. Okay, why it is codebook? Because if you remember, we had electronic codebook mode, the very first mode, ECB mode, and we said we should not use it. Why? Because codebook simply means that you take a number and you go to the book and look up the output. That's all we are doing here. So if you really look at this picture, you take the plain text and you are going to look up the output. So this is actually Codebook, except that it is tweaked. So the book changes every time you go to look at it. Right? So this is a tweaked Codebook mode, and then ciphertext stealing is here, and XOR, encrypt XOR is, as you see, this one. Alright, since this became a IEEE standard, then NIST made it a standard as well. I don't have the NIST number here. This is the IEEE standard number. It is 2007. So that means it is very recent. And just after that, NIST made it a standard. I don't have the number here, but it is in the book, the NIST standard number. Anyway, the one more detail is that the polynomial that is used for Galois field 2 raised to 128 is this polynomial. Okay, x128 plus whatever number this here, right? The advantage of this whole mode is that you can do everything in parallel. So all these blocks can be done in parallel except for the last one. I mean, the last two blocks, but they basically, so you do them and then you cannot transmit the last one block until you do the last one. But most of it is in parallel. So this can be done in hardware as well as software. And then you can random access. Again, random access applies to all the blocks except the last block. And obviously very few chances that you will want to read just the last 8 byte for something. You probably want to read the whole block, or you probably whole sector as well. And has both nonce and counters. So nonce, anybody remembers what is a nonce? Just once, right? So you never use any of the numbers here again. I is not used again, J is not used again, and everything else. And both of them also use count and look like a counter, I and J. So defined that is okay. Now it is implemented, although it is so new, but it is already implemented in packages that you can use. For example, TrueCrypt is a package which you can use to encrypt your disks. Once I was looking into this area, and I found TrueCrypt is a public domain software and is very highly secure. And they were giving a story that some particular drug dealer's disk the FBI got, but they could not decrypt it. So that's a big positive about it. Anyway, so this is strong. Basically, it is free. Biggest thing, it is free. FreeBSD, OpenBSD, soft-RAID encryption software, they all use this. And it is also used in Mac OS X File Vault, and it is also used in hardware devices, Kingston, Data Traveler, and so on and so forth. And so the summary is that even though it is very new, it has gotten into the real world. Any question about this? All right, so let's summarize this whole thing, and I thought it would be good to give a graphical summary of all the modes rather than textual summary. So first of all, we talked about 3-DES, and remember in 3-DES we use EDE with 2 keys, and that gives us close to 112-bit protection, not exact 112-bit, but and that is what you will get with 3 keys as well, and that is, I mean, if you use just the 2-DES, you will get half of that. So 3-DES, the best compromise is to use EDE with 2 keys, most popular version. Then we talked about the mode. The first mode was ECB, electronic codebook, which means that you just take each block and you just use the same key and you get a ciphertext. Well, that is not recommended because it is very easy to break, because you're just giving the attacker too many data points to fit with the same key. And one of the rules in encryption is, and we'll keep repeating it many times, is that you don't use the same key again. All right, so that was that. So now we have all these modes. This is block chaining, ciphertext block chaining. Actually, it doesn't really show correctly because we would be chaining it to the next block. But anyway, so you take the ciphertext from the previous block and chain to the next block. Ciphertext feedback mode, where you take the ciphertext and you feed it back to the top. But the problem with that was that you could not generate the whole thing before you have the plain text. So they said, okay, let's not take the feedback from there, we took take the feedback from here. And so that made it output feedback mode. In the output feedback mode, the plain text can come at the last second, and basically you have the whole thing ready to encrypt, pre-computed. And then finally was counter mode, which is very similar to the output feedback, but you don't even take the feedback, you just have a counter which keeps going up, and then you encrypt it, and so with the key, and then you keep the stream ready for use. And then XTS-AES mode, in which I have shown just the first block, the last block has more details. Alright, so these are total 6 mode, 5 pictures plus 1 here, ECB. So, yeah.
So, like, all these encryptions that we're talking about, like the keys keep on changing, how do they decrypt it?
How do they decrypt it? Oh, yeah. See, all of these are invertible in the sense that you can see any of the modes you go through, the reverse process is exactly there. So, with the original key, you can come back. But if you were to just take any block and try to break it, you really need all the blocks to decrypt. I mean, in this case of ciphertext chaining. In the case here, you need the whole stream to get that and all that. So decryption is all basically you just generate more keys with the old keys, but the method of generating the keys is so random that itself is a problem to be broken. So you don't get the second data point with the same key. I mean, in that sense, is that the next block is with a new key which is derived from the previous key. So you do derive the keys from the keys. For example, DES, 16 keys were derived from single key, but not the same key was ever used again.
So how would they decrypt it? If
Oh, decryptor is the same thing. The decryptor has the same algorithm to generate the keys.
okay.
Yeah, I mean, key generation from a key is very common thing. So you will see that throughout. In DES we do it, in AES we do it, and here we are doing indirectly something similar. So the decryptor has to be able to see that algorithm is okay. So a attacker can probably derive the keys, but then if they know the original key, right? But if they don't know the original key, finding the original key first and then deriving the keys and trying to check out with the other thing is a lot more work. Okay. All right, that brings us to homework number 6. And the homework is for each of the modes. Now I have written the whole problem text here, which could be different in your book. What we ran into the problem is that the book has 2 editions, international edition and the US edition. The problems are different. And to just avoid any confusion, here is the problem. This is the final problem. If your book says something different, don't use that. Use this. Okay, so the problem is for each of these modes, ECB, CBC, CTR, identify whether the decrypted plain text P3, block P3, so we just talk about the third block, will be corrupted if there is an error in block C1. So the first block gets corrupted in transmission, but the plain text 3 will be corrupted. And obviously you have to explain why, if it is corrupted. If it is not corrupted, explain why. Now, assuming that the ciphertext contains n blocks and there was a bit error in the source version of P1. Now this is different. Here the bit error was in the network transmission. Here the bit error was inside the computer. Before the plain text came about, 1 bit was wrong. Right? Identify how many ciphertext block this error will change. Okay, the problem is clear. You just have to see how much, how the errors are propagated.